All right, welcome everyone. Once again, my name is Matt. I'll be hosting today's presentation. And today we're going to be talking about the different panel type options in S-Frame. And I do also want to preface this webinar by saying that this is part of a three-part series of webinars that are all what we'll call coffee break style webinars. So they're meant to be shorter, more to the point, less slides, more actual presentations. So if you've attended webinars from us in the past that were perhaps a little bit longer, this is a little bit different than that. Just wanted to set the expectation in advance. So we're going to introduce a bunch of different panel types and maybe describe different scenarios where you might want to use one versus the other, how they can be defined in S-Frame. And we have a few minutes at the end for Q&A as well. I'd just also like to introduce myself. My name is Matthew Sauer. I manage the global technical team responsible for the S-Frame software products. You've probably heard my voice before if you've attended S-Frame trainings or previous webinars, and I'm based in Vancouver, Canada. So let's just jump right into the presentation of the software here. So I've got this model open, and this is going to be kind of our demo model for today. So as you can see, I've got a grid of columns supported by a grid of beams, and I just want to look at different types of panels. So really, I'm going to be working mostly in the geometry window here. This is the window that's used to define and edit geometry in our model. And for the most part, I'll be working within the panel element tool as well. And I'm going to start by introducing here, by actually just click on the display legend option here. When I click on the panel element tool, it gives me the ability to see this legend. If you don't see this, again, just toggle on the display of the legend. It's this rainbow colored icon at the bottom in the status bar. And you'll be able to see a pretty long list of different panel types. So we have a few that we're going to go through today, and a lot of them are somewhat related to the ones we'll be talking about, but they may not necessarily need a deep dive. It's more so just a variation. As you can see, we've got a bunch of different mesh panels, and we can certainly dive into that more in training courses and so on. But let us just start with an area load only panel. Let's just envision a scenario where we might have some fairly non-significant portion of our structure that we didn't actually model in the structure. Maybe it's some steel grating or something that is relatively light and not fairly structural in its nature, but we want to represent the load distribution that it allows us to define. So we can do that by defining an area load only panel. And so I'm going to actually just click on this option here. I selected the panel type by left clicking on the colored box next to its name. I could have also just selected from this drop-down list of the panel types here in its status or in the data bar. Each one will give me the same kind of controls, and then I'm just going to sketch this out. So here I'll just left click to basically draw the perimeter of my area load affected area. So I'm just going to left click and draw that in. You can see it started when I was drawing, it was kind of shading that in with purple. And I can actually shrink my elements for visual checks with this option here at the bottom of the screen. And I'll be able to see here that it's basically shrunk that in. And this just allows me to see if I have any overlapping elements, like for example, my panel edges might overlap with my members. It can be hard to identify those if we're not shrinking those elements. But when I shrink them for visual checks, it's a lot easier to see. So I like to use this from time to time. Sometimes I even just leave it on. Might not be everyone's preference, but it's something you can certainly do. You'll also notice here that we have this little node in the middle that didn't exist before. This is called the panel handle. And one of the reasons that we have this in S-Frame is because if we have a panel that overlaps with our members, for example, or perhaps other panels or just other objects in general, it may be hard for us to distinguish applying properties to that panel versus the other objects that are overlapping with that panel. So this just gives us an insertion point for different properties where we can just left click and apply it to this point here, this node rather, and it's going to apply it to the rest of the panel. So I've told S-Frame that I want this area to be part of my area load only algorithm, I guess, for lack of a better term. But I also need to tell it which elements I want to conclude in this type of area load distribution. So I have this folder that's included with every single S-Frame model. It's called the area load members folder, and I can left click on it and I can see that it's currently empty. So maybe I'll just go to a top-down view in my area load view. Here I can see my kind of plan view of my structure. And at this point, I could then go into the selection tool and say, okay, well, which elements do I want to be part of this area load members folder? I can select either all of the members, like so. I can select or unselect certain elements, like maybe I just want to exclude certain ones in a certain direction. Any of the elements that we don't want to accept those area loads, we can exclude from this selection set. So for example, we might have horizontal bracing, for example, that's only meant to resist lateral loads. We could exclude that from the area load members folder if we wanted to. I'm going to make it simple on myself today, though, and I'm going to select everything when I open up this area load members folder. And I'm just going to right click, and I'm going to say update the open group with the current selection set. So I've done that now. And I go back to my structure, and I can always verify this. Maybe I'll just switch to 3D here. I verify this by just clicking on this again, and I can see all my elements are selected. And I know that because they're appearing as this solid blue lines and dots. Now I've got my area load members defined. I've got my area load panel defined. And the last step in this process is to define the span direction tool. The span direction tool allows us to characterize whether we have a two-way span or a one-way span and which direction that span might be. In this scenario, I've got pretty square, polygons in my framing here. So it might not make a big difference between long and short direction. But I can actually just click on the two-way option, for example, and left-click and apply that to this panel handle. And we get these pink lines that appear, and those show up as the boundaries of each area load member's tributary area. So not surprisingly, the edge members are going to have half the tributary area of the interior members. And this is with a two-way span. I could switch to a short one-way span. And it's going to use the geometry of my elements, and it looks like I might have minor variations throughout each span here. But it's going to allow us to control that. And if I did want to align these, I could either break them up into individual panels for each polygon, or I could use this any option that allows me to span between two predetermined joints. And a nice part about this, if I just maybe switch it back to the two-way span here, is I can go into the loads window and I can say, here's my test load case. And I want to have an area load using the area load tool. I want this to have a magnitude of -10 kilonewtons per meter squared. And I just click and apply it to that panel handle. And what it's going to do is it's going to basically break that down into member loads that are apportioned based off each member's tributary area. Now we can't see this until we run the analysis, but if I would prefer, I can get rid of this member load here, or this area load rather, and I'm going to just toggle on display of my member loads so that when I apply this another way, I'll keep the same magnitudes, but the only thing I'm going to do differently here is I'm going to convert those area loads to member loads initially when I'm actually applying them. So I can click on this option here, say -10 kPa, just like I did before. And now I can actually see all those magnitudes of those member loads. And they're actually produces member loads for me automatically now. So it just helps us to be able to see this before we actually go in and run an analysis. I'm going to get rid of these loads here just because it's not really part of the rest of my presentation. So we can get rid of them. And now we can look at the panel tool again, but this time we'll look at a different panel type. And this may actually be a good segue because right now we do have our area load panels defined and we have these span directions, but let's just say that we did actually want this panel to have some stiffness in the lateral direction to represent a rigid diaphragm perhaps. So we can do that by clicking on this rigid diaphragm panel option. And I select that colored box next to the name of the panel. And then I just go ahead and I apply the property to that panel handle. And you can see it changed the color of that panel handle. And with that, it's changed obviously the color of the outline as well. And this is giving it rigid diaphragm properties, but it's still retaining those original area load span directions as well. So I have those abilities to apply those out of plane loads to the framing underneath this. But in the plane of the diaphragm, I have a rigid diaphragm. So what this means here is that I have this basically constrained set of joints. All the members within this diaphragm constraint along the edges or within the interior of this panel are going to be constrained to act rigidly in the plane of the diaphragm. So that means in the X global direction in translation, the Y global axis in translation, and rotation about the z-axis. Rigid diaphragms, however, don't have any out-of-plane stiffness, so that's a note to keep in mind, and you'll see a difference in a different type of diaphragm shortly. You can also actually verify which nodes are constrained by the diaphragm by clicking on this Verify Diaphragm Nodes button, and you can see all these pink dashed lines all converging on this one point at the panel handle. So what we usually do with diaphragms is when we create them, we'll nominate this joint, which I'll go to do that right now, under the Edit menu, Analytical Model. We can generate a rigid diaphragm mass joint. Now, if we run an analysis, it will do this automatically for us, but this just allows us to prepare it in advance. And this is just showing me that the center of mass location has been recalculated to coincide with the geometric center because I don't have any thicknesses or anything to denote any variation in where the center of mass would be compared to the center of the geometry. So I'll click OK, and it gives me this little red node in the center of that joint there. And that red node is now my rigid diaphragm mass joint, and it's basically the leader of all the other joints in that diaphragm constraint. So if I were to apply a lateral load, for example, let me just go ahead and do that right now. Apply a lateral load in the x force direction of 10 kilonewtons. I'll apply it right there. And I go ahead and run an analysis, linear static analysis. I'm going to get a clean solution, which is always nice to see. And now I can look at the deflections, and I can see, if I maybe just display my numerical values for displacement, this is pretty small displacement values, but I look at the properties, it's 0.0685. Just look at a few different spots. You'll notice here that we're getting the same deflection in the x direction for all of these joints. And what else is kind of telling of this behavior? So I look at the axial force. Despite the fact that I'm applying some lateral forces, none of my beams have any axial load in them. And that's because they're all constrained to act as a rigid set in plane. But if I were to apply a load out of plane, there would be no rigidity to that diaphragm. It doesn't have any rigidity out of plane. Now you're also noticing here that right below this rigid diaphragm, I have a general diaphragm. So general diaphragm effectively provides the same outcome as a rigid diaphragm, but it's done a little bit differently. Whereas a rigid diaphragm will constrain joints only within its boundary or along its edge, the general diaphragm allows you to just basically define a smaller selection set. So if I can get rid of this guy here, get rid of that diaphragm node as well, I can go into the panel element tool, switch to the general diaphragm, and I'm just going to say, I'll just define the general diaphragm just on this one corner here. And it's going to look at all the other joints that share that same Z elevation, basically that same plane, and it's going to constrain those joints as well. So it just allows us to not have to define quite a great area, or a larger area for our panel, but still constrain all those joints. I don't typically see people using general diaphragms as much as rigid diaphragms, but if you did have a lot of joints to constrain within a certain area, it could be pretty handy. Moving down this list here, we're going to jump around. So we're not necessarily going in order, but I'm trying to keep it in kind of a logical rhythm, let's say. We have another diaphragm type called the rigid body diaphragm. And you may be wondering, okay, this sounds very similar to the rigid diaphragm or the general diaphragm, which is effectively a rigid diaphragm just with a different way of constraining or selecting which joints are constrained. So this will effectively do the same thing as what we were doing with the rigid diaphragm, with the exception that it's also constraining the out of plane degrees of freedom as well. So this is making basically that layer of joints fully rigid in and out of plane. If you had an application for that, you could certainly look into what that might bring for your model. So if we go back here and I apply, well, I'll go and actually generate my mass joint here. Give me 1 second to create that for myself. And I go to the loads window and I apply another 10 kilonewton load right here, run an analysis, and let's see if we're getting anything different. And what might be a little bit more interesting is if I actually apply the loads out of plane as well. So here I'll look at the displacements, and you can see this is staying totally rigid in the kind of vertical plane. But maybe to add a little bit more intrigue to this, let me go ahead and apply a load in the Z force direction. I'll just apply it right here. just to give it a little bit more interesting. Run an analysis, and let's see what we're getting out of this. We may not get large deflections, but we should notice at least an unusually different deflected shape. And you can see here, it's very small. If I look at the DZ values, we are getting different DZ values throughout each joint, but it's effectively making it a fully rigid plate rather than the rigid diaphragm, which doesn't have any rigidity out of plane. Now, the fact that I also applied that lateral deflection, we lose some of those vertical deflections in the details. So let me get rid of that here, just so we can really observe that a little bit more clearly. I know I'm running a lot of analysis here, but I think this might be a better visualization. And here we can see, if I just look at one of these side views, we can clearly see that that joint is lifting up, but the rest of the joints are encouraging it to behave as a fully rigid body out of plane. So moving on even further here, we're going to switch this up here. So I'm going to get rid of this panel, which is going to get rid of all those diaphragm constraints. And I'm also going to get rid of that rigid diaphragm node. So what I do to do that is I click on the joint tool, and I hold down the control button on my keyboard, left click and drag, and it's going to get rid of any stray nodes that I would have dragged around. The control button basically activates the opposite functionality of whatever the tool I'm using would have originally done. So that tool originally, this tool here, the joint tool would have originally created joints. When I hold control and click and drag around those joints, it actually deletes those joints, but only the ones that I've selected and only the ones that aren't attached to other objects. So now we're going to change gears here, and I'm going to look at a different panel type. And this one here encompasses a lot of the different variations that we've seen already. I'm going to use the shell mixed mesh panel, which is the most, for me personally, the panel type that I use the most in far as the meshable types are concerned. So here I'm going to define some properties. I'm going to define a thickness. I'll say that it's 200 millimeters thick. And I'm going to define a material property. Say it's the concrete material property that I have in my default list. And there are some other parameters. So we have this mesh density. We have a seed density, a quad weight, and a few other parameters here that we can look into. I'm actually going to start by just drawing this out. So I'll just left click here and draw this out around the extents of my area that I want to apply this to. You can see it's inherited those colors indicative of the shell mixed mesh panel. And I can actually verify some of the properties that are applied using these different display options. So anywhere you see some text and then a glasses icon next to it, you'll be able to turn on or off different display toggles. So here I've got the display thickness toggle, which allows me to display the thickness for that panel, which says 200 millimeters. I can also see the mesh density toggle, which I'll explain right now. Basically, the mesh density allows us to control the number of shell elements in this case, because this is a shell mixed mesh panel, meaning it has a mix of triangular and quadrilateral elements. It allows us to control how many elements we have along the longest edge of the panel. So this is clearly the longest edge of the panel. So I have 4 spans effectively, and I could go in and control. If I have 10 elements, that will basically be what I'm getting out of this because I have a mesh density of 10. If I want to increase that, I could increase this mesh density and apply that property here. We also have a seed density, which controls basically the factor increase in density around the internal nodes in our mesh, which might be these nodes in around our columns, for example. And then we have this quad weight percentage. And this allows us to control an approximate kind of bias towards having quadrilateral elements versus triangular elements. So S-Train's meshing algorithm will aim for 90% quadrilateral elements. It's not going to sacrifice mesh quality to achieve that, but it's going to shoot for definitely a bias of quad elements versus triangular elements, which most of our users will prefer. And as you can see, there are other types of panels. Like we have, these are mixed panels, mixed mesh panels, so mix of triangular and quadrilateral. We have quad panels, and we have triangular mesh panels as well. In addition to that, we have shell mixed mesh panels, we have plate mixed mesh panels, and membrane plate mixed mesh panels. So shells are basically the elements that we're going to generate from the mesh, and those will have in and out of plane stiffness for the elements that we create. We have membranes, which are only in plane stiffness, so good for fabric structures, for example, or very thin structures that might rely on just their tensile or even compressive stiffness, if that's what you wanted. And then we have plate mixed mesh panels, which only have outer plane stiffness, rather, and no in-plane stiffness. And we've seen those used for like very thin floor systems, but in general, the shell mixed mesh panel is kind of the jack of all trades when it comes to most of our users' requirements, because most applications that we found in civil engineering require you to have in and outer plane stiffness. But if you don't, you can always look up those other options. So here, let's just mesh this panel with the parameters that we have. So 10 mesh density. I'm going to click on this button here that says mesh panel elements of type membrane, plate, or shell. And it's going to generate for us a mesh. And I'll admit right away, it's not a beautiful mesh, but it's just using the default parameters that we had. And we can certainly revise those. It's giving us the option to accept this or not. I can click no, I don't want to accept this. And my next step might be to increase the mesh density. And that will just create smaller elements along the longest edge, and obviously the other edges will be apportioned respectively. So here, I'm going to change here the mesh density. I'm going to say, let's use a mesh density of 20 instead of 10. And I could go in and I could apply that property just now, like I would for everything else, any other type of panel rather. But I'm actually going to give you a bit of an introduction to these modify options, because we can modify everything here. So I could modify my thickness, my material, my mesh densities, and so on. Or I can just say, I just want to modify the mesh parameters and keep everything else the same. And this can be a handy setting if you have a bunch of different panels with different thicknesses, maybe different material properties and different mesh parameters. And you can really fine tune which parameters you control or which you adjust based off of the entry there for the modified setting. So I'm just going to left click and drag around this panel handle. And now it's inherited that new mesh density. But you'll notice it hasn't changed anything else. Like the seat density is still 1. The thickness is still 200. So we don't have any issues with those parameters. So I'm going to go ahead and mesh again. And you can see now it's producing a much more regular mesh. We have 20 elements along the longest edge, and we could count the number of elements along the other edges here, and we get a better idea for what's happening there. So this is generated for us shell elements that are basically have the desired stiffness and mass that's controlled by the material properties that we've defined, which was concrete in this case, and the thickness that we've assigned, a 200 millimeter thickness. And it's going to allow us to approximate things like slabs, like walls, foundations, maybe plates for smaller applications. And SGM has very powerful mesh generation settings or abilities, and a lot of abilities to control these meshes and extract information from them for design and so on. Now, if you were the type that didn't want to use this, what I'll call auto meshing process, where we define a panel, we define the parameters related to the panel, and then we press a button to mesh it. If you want a little bit more control, you can certainly do that as well. So I can get rid of this mesh by just clicking on the quadrilateral element tool, because it's created quadrilateral elements. I can left click and drag with the control button down, and it's going to get rid of all of those quadrilateral elements. But you see it's left behind a bunch of joints that are now orphaned, so I can use the same process for the joint tool. Hold down control, left click and drag, and it's going to get rid of all those joints as well. And now I can look at another option where I can click on the quadrilateral elements tool. And within this tool, I have a bunch of different parameters that allow me to define different properties. So I have obviously my thickness, I'll say 200 millimeters. My material properties can still be defined. I can define pre-stress as well if I wanted to. And I'm just going to draw in a panel, or not a panel rather, one large shell. So go a shell right here. And I needed to define 3 points to basically to sketch the, or sorry, 4 points to sketch the outline of that. And this is one large shell, but you may remember when we meshed, we actually discretized that so we had more elements. But if we had a specific reason to maybe control our mesh in a certain way, like we wanted to have every 1 meter, we had a new element, this might give us a little bit more control over that, but it requires a lot more manual driving of the process. So I could say here, I've got this this shell, and maybe I'm going to draw another one in the polygon next to it. So I got these two shells that I want to basically break down into smaller shells. So I can do that using the subdivide command, which is this little division symbol here. I can also get that from the edit menu, subdivide. And here we have control to basically break up these elements. So this is a quadrilateral element. So this is where I want to actually control that information. And we can see we have control over the ij direction, which is the local coordinate system, basically saying from the start joint to the second joint, and the jk direction, which is from the second joint to the third joint. For each one of these, I can control how many links I've created. Now we might want to actually verify which direction is the I and j joint directions. So I can display my local coordinate systems for these shells, and I can see that the local x-axis will always go from the I to the j direction. So that would say that for both of these shells, the I direction is, the I joint is here, the j joint is this joint here, and this one here, it's the I joint, j joint. Now we can control the orientation of the coordinate system. We can adjust it if we need to, but it's always good to know that if you're working with this process, because I can then go into the edit menu, and then I can go to subdivide, and I can say, okay, I want to break this up. And I'd say that in the I direction, ij joint direction, I have 5 links, and in the jk direction, I might have 4 links. I click OK, and it's going to break that up into shells. And those shells can be controlled based off of their discretization, however much I like. So I can say I want, 20 subdivisions per span effectively, if that was really what I wanted to do. The downside of this process is that it's not going to automatically connect internal seed nodes or joints or anything. And it's not so handy if you have multiplanar mesh that you want to connect those joints, because shell elements and members and so on, they only really connect at shared joints. There are some caveats to that. We do have different constraints that can control that, but that's kind of a general rule of thumb to keep in mind. So that's a quick dive into some of, not all of the element types under the panel element tool, and also quadrilateral element tool. We also have triangular elements if that's something you want to do. It's the same process, but at this stage, I think I want to just open up the floor for the Q&A. So let me just get back into my slideshow here. Give me 1 second. Make sure I'm showing the correct slide. And we do have a few minutes for questions here, so I'll try to answer some of the ones that came in. A few of you also sent emails with questions kind of in advance, which is really handy for me because I can look into it beforehand. Some of these I have to answer off the top of my head, so I don't always know the answer. But let's get started with that. So what if my area load panel doesn't work or is turning red? So that's actually a common support question that we get. So let me just try to go back here, and I'll get rid of these quadrilateral elements by using the quad tool and getting rid of the joints as well. And we'll change this back to area load panel. Make sure I've got that here. Oh, I've got to modify the panel type. And here, if I were to define the area load members in such a way that it wouldn't be able to break down those different span directions, rather, I could see if I could make something that might not work for me here. Let me just try this out here. This is a bit of a live trial, so I don't know if this is going to necessarily do what I'm hoping, but let's see. My goal is to kind of break this algorithm here, so you may not always want to do that. Yeah, so it doesn't seem to be working the way I hope, but basically, if SStream can't find like a polygon, for example, that would represent your span directions or your spans, I suppose, and the members supporting those spans, it will show up as red with this algorithm. We actually produced a video that I'll try to link in the chat afterwards, but if we look for span directions in the help system, a lot more information about why these might not decompose and what happens. So this is actually a couple of different examples. And then you'll see here further down what it looks like if they don't span. It's going to show up with red. So there are a bunch of different examples. One of them being like, in this case here, we have a concave subpolygon that isn't amongst the different shapes that we can support. We've gradually removed different conditions that have to be met because we've improved the algorithm, but you may still find some that don't always work. And check out our YouTube channel. If you go to Altair How To and you search for air load panels, you'll find lots of information there as well. Okay, next question here. What's the difference between a rigid diaphragm versus a rigid body panel? So maybe just quickly I'll touch on that because we did go through that demo. Rigid diaphragm panels have in-plane stiffness only, being the plane of the diaphragm itself, versus rigid body panels have in and out of plane stiffness, and it's fully rigid in both cases. It's just which degrees of freedom are rigid and constrained. So that's the difference. Rigid bodies fully, all 6 degrees of freedom are rigid, versus rigid diaphragms, it's just the in-plane degrees of freedom. Last question here. Why would I draw shells manually versus auto meshing? I tend to mostly steer towards auto meshing, maybe just out of habit. I've found that I get to know the algorithm pretty well, and I can control it with the different parameters. But if a user does have a requirement to keep nodes at every 1 meter or every 50 centimeters or something like that, you can certainly control it more precisely with the method I showed at the end, where you define one large shell and then you subdivide it and use that number of links to control the spacing. Now it's going to give you even spacing versus other like the mesh auto mesh process with the panel elements will actually vary the spacing potentially based off of the geometry. But that's one reason why you might want to do that. Again, with the caveats that it's not going to be automatically looking for overlapping the nodes of your columns and your shells, for example. That's something that the meshing algorithm takes care of. But if you use the manual approach of subdividing your shells, it's not going to look for that. All right, I think that was the end of the questions that I had. Sorry if I missed any of them, but I did want to thank everyone for their time today. I hope you guys enjoyed this session. We are going to have another session next week, so you can stay tuned for that. That's looking into generating shell element meshes basically out of members, and it's a nice workflow that we've never really talked about in a webinar, given it, I think, the appropriate attention. So it can really take what we've learned today to the next level and take some of your member models and represent them in 3D, for example. So if you're interested in that, that's next week at the same time. We hope to see you there. So enjoy the rest of your day, and again, we'll talk to you next week.